Have you ever wondered why apples fall straight down and not sideways? This seemingly simple question led to the discovery of one of nature's most baffling phenomena, gravity. For centuries, gravity was viewed through the lens of Sir Isaac Newton, an invisible force that pulls objects towards each other, acting at a distance. It explained why we stay grounded on Earth, why the moon orbits us, and even why the planets follow their paths around the sun. Newton's law of universal gravitation was revolutionary, yet it left many questions unanswered. How does gravity actually work? How does it communicate across the vast emptiness of space? These questions remained a mystery, with gravity being the enigmatic puppeteer controlling the motions of the universe from behind the scenes. But what if we told you the reality is far more complex and fascinating than that? Stay tuned as we delve deeper into the enigma of the universe and how Albert Einstein's theory of general relativity reshaped our understanding of gravity. Enter Albert Einstein, who challenged the very foundations of our understanding of gravity. In the early 20th century, this visionary physicist came forward with a radical proposition that would forever alter our comprehension of the universe. He introduced a theory that was drastically different from the established Newtonian view of gravity. You see, Sir Isaac Newton described gravity as a force acting between two bodies. In this view, an apple falls from a tree because the earth pulls it down. But Einstein, he had a different take. He proposed that we don't live in three-dimensional space, but rather in a four-dimensional space-time. Think of it as a cosmic fabric that encompasses the universe. And here's where it gets interesting. According to Einstein's theory of general relativity, this fabric of space-time isn't just a passive stage on which celestial bodies perform their cosmic ballet. No, it's an active player in the dance of the universe. Einstein suggested that mass and energy, the stuff that makes up everything in the universe, from the smallest particle to the most massive star, warp this fabric of space-time. The more massive an object, the more it distorts the space-time around it. This distortion, this warping of space-time, is what we perceive as gravity. So in Einstein's view, the apple doesn't fall because the Earth pulls it down. It falls because the Earth warps the space-time around it, creating a path that the apple naturally follows. A path that we interpret as a downward fall. This was a paradigm shift, a complete reimagining of gravity that moved us away from Newton's force-based perspective to a geometry-based view of the universe. A bold step that, while initially met with skepticism, has since been validated by numerous experiments and observations. So, what does this warping of space-time really mean? It means that we're living in a universe that's far more intricate and fascinating than what meets the eye. It's a universe where the fabric of reality itself bends and twists under the weight of mass and energy. A universe that's not just a stage, but a participant in the cosmic dance. Picture a stretched rubber sheet. Now place a heavy ball in the middle. You see that ball warps or distorts the flat rubber sheet, creating a dip or a well around it. This is a rudimentary but useful analogy to help us visualize the complex concept of space-time curvature in Einstein's theory of general relativity. Imagine the rubber sheet represents our universe's four-dimensional space-time. The heavy ball symbolizes a massive object, like a planet or a star. As the ball rests on the sheet, it creates a depression, a curve. This curve is not just a feature of the sheet, but an inherent change in the space-time fabric around the mass. Now, if we roll a smaller ball, let's say a marble, near the depression, it will veer towards the larger ball, not due to any mysterious force pulling it, but because the path, the geometry of the rubber sheet has been altered by the heavy ball. This is analogous to how gravity works according to general relativity. Objects with mass and energy, from tiny particles to gigantic celestial bodies, distort the space-time around them. Other objects moving nearby are not pulled towards the larger mass by a force. Instead, they move along the warped paths in space-time created by that mass. This is why our Earth orbits the Sun, why the Moon orbits the Earth, and why we feel pulled towards the ground. It's like a cosmic dance choreographed by the mass and energy of the universe, shaping the stage on which all matter and energy move. The paths we take, the orbits, the falls, the flights, they are all etched into the space-time fabric, guiding us along the routes determined by the universe's mass and energy distribution. In essence, objects don't fall down. They follow the curves in space-time created by mass and energy. It's all well and good in theory, but does this space-time curvature have real-world implications? Well, indeed it does. In fact, something that many of us use daily, the Global Positioning System, or GPS as we more commonly know it, wouldn't function without accounting for space-time curvature. GPS satellites orbiting the Earth are further from the planet's mass than we are on the surface. This means that, according to Einstein's theory, time actually ticks slightly faster for them than for us. Now, you might be thinking, surely a fraction of a second won't make much difference? But when it comes to GPS, even a tiny discrepancy can result in huge inaccuracies. If the GPS system didn't account for this time difference, we could end up miles off course. So, the next time you use your GPS to find the quickest route to your favorite coffee shop, remember, you're relying on the principles of space-time curvature. But let's shift our gaze from our everyday lives to the cosmos. It's there that we witness another fascinating phenomenon born out of space-time curvature: gravitational lensing. When light from distant stars passes near a massive object, such as a galaxy or a black hole, the space-time around that object is curved. This causes the light to follow a curved path, much like a marble rolling along a curved bowl. As a result, the light from the star bends around the object, creating a lensing effect. This phenomenon allows us to observe galaxies that would otherwise be hidden behind massive objects, and even gives us clues about dark matter, the mysterious substance that makes up about 85% of the universe's mass. In essence, the curvature of space-time works like a cosmic magnifying glass, revealing the unseen corners of the universe. Indeed, our everyday lives are subtly but profoundly influenced by these cosmic gymnastics. From apples falling to the ground to the bending of starlight, the concept of space-time curvature weaves a fascinating tapestry. We've journeyed through the enigma of the universe, grappled with the titanic clash of ideas between Newton and Einstein, and dived into the rubber sheet analogy, a brilliant conceptual tool to visualize the warping of space-time. Let's take a moment to summarize what we've learned. Our journey began with Newton's law of gravity, a concept so ingrained in our understanding that it's hard to imagine a world without it. But then, along came Einstein with his revolutionary theory of general relativity, challenging our perceptions and reshaping our understanding of the universe. He proposed that it's not some mysterious force pulling the apple down, but rather the apple following the curves in the fabric of space-time created by the Earth's mass. This shift from Newton to Einstein marked a profound transformation in our comprehension of the cosmos, one that required us to rethink the very fabric of reality. It's a shift from seeing gravity as a force to understanding it as a curvature, a warping of space-time. We also explored the rubber sheet analogy, a visual aid that gives us a glimpse into the invisible world of space-time curvature. Imagine a stretched rubber sheet representing space-time. Place a heavy ball on it and it creates a depression. Now, if we roll a smaller ball nearby, it will naturally roll towards the larger one, not because of an invisible pulling force, but because the larger ball has distorted the sheet's flatness. But this isn't just abstract theory. The concept of space-time curvature has real-world implications, influencing everything from the path of a photon to the orbit of planets. It even impacts the precision of your GPS. Next time you see an apple fall, remember, it's not just falling, it's following the curves in the fabric of space-time. The universe, it seems, is a rather curvy place.